bargaining solution, etc. So we looked at this problem from a cooperative game theory point of view. What can be called cognitive and what cannot be called cognitive is one that generates infinite amount of discussion, so I have my own ideas about it, and if I need to summarize, it's the following. First of all, some of my early students and I used to have these conversations, and then at some point I said, I don't want to be the cognitive police, and I don't want to to be the one to decide what can be called cognitive, what cannot. That's the first. The second is, we shouldn't fall in love with a buzzword. Cognitive is just a buzzword, right? So it's going to go. Someday people will stop calling anything cognitive, and we'll just think it's silly and passé. So doesn't matter. What really matters is that the use of this buzzword and the fact that people ended up coming together around this concept has helped radios and networks move into a more adaptive, a more dynamic, and a more efficient way of doing business. That's what ultimately we should care about, right? It's useful to say cognitive because it's a shortcut, and people say, oh, okay, cognitive radio, yeah, I'm interested, or I've read about it, and so on. But I'm all for a fairly loose use of the term, because the term to me doesn't really mean anything ultimately. The only thing that means anything is what you really can achieve in terms of making a better network. So, but this sort of discussion persists. So you send a paper sometimes, and people say, "Oh, but this is not cognitive," but that's life. Sometimes you send a paper that's very cognitive, lots of artificial intelligence in the decision making, things that are really, if you read Mitola's thesis, that's exactly what he meant, which, by the way, is not dynamic spectrum access. But you send a paper about that, and you don't include dynamic spectrum access, and then the reviewer says that's not cognitive because there is no frequency agility. So there's no real way to win those sorts of arguments because they are kind of meaningless. They're totally semantic arguments. So I think you have to try to make a case on the basis of more kind of philosophical ideas about efficiency and about dynamic adaptability. Okay. What are the typical results of game theoretic analysis? So in a game theoretic formulation of the problem, we're really often looking for the equilibrium. So what's the point that once reached by the radios or by the networks, they're stable, that there is no incentive for any of the participants to deviate from that point. So when you hear about Nash equilibrium, that's what the Nash equilibrium is, the point from which there is no incentive for anyone to unilaterally deviate. You are also looking for convergence properties. Is there a way that these agents in the cognitive network or the network of cognitive radios can arrive at these points of equilibrium in an independent, autonomous way? So can they converge through some process of reasoning? In the case of cooperative games, what's the outcome that you expect from this process of bargaining among the players? And many times you're interested in the design of incentives or disincentives for use of the resources. So many times the only way to really achieve efficient use of resources is if you have an explicit set of incentives, often economic incentives, where you say, okay, you want the resource, you have to pay for it. And then you look at the design of auctions, the design of pricing mechanisms, etc. So anyway, that's game theoretic type of analysis. The other thing that you often see in the literature in terms of an approach to radio resource management, to solving a radio resource management problem, is the use of heuristics. Once the problem is not simple enough that can be solved in some reasonable amount of time, you apply some heuristics. The problem may be too complex to find the true optimum. The environment may change too rapidly, so sometimes it doesn't make sense to find the optimum point of operation, because once you find it, the environment has changed and the optimum is no longer optimum, so you're chasing something that will never truly be optimal. Sometimes you're trying to allocate resources and make decisions without knowing the full picture, so you have partial information with which to optimize your function. So you have to use some sort of heuristic to deal with this lack of complete information. And sometimes you find a heuristic solution that can be shown to do not much worse than the optimal. So sometimes you can actually calculate the optimum and say, okay, here's my heuristic, and I can prove that most of the time the heuristic is really, really close to the optimal, and it's much easier to solve a solution. So, of course, it's not very valuable to just throw a heuristic out there and say, okay, this is my heuristic, unless you do some of these things, right? Unless you really show that you're bounding the difference between the heuristic and the optimal, or some other good properties of the heuristic. So, for instance, a heuristic may allow you to approximate an objective function so that it becomes linear, or at least the problem becomes convex. And these approximations may be valid under some subset of conditions that you need to specify. So maybe those are good approximations as the number of channels increases, or under high signal-to-noise ratio, etc. And sometimes you can show that simple adaptations can give good results with high probability based on only local conditions, rather than taking into account the full global conditions for the optimization problem and so on. So there are sometimes that you can apply heuristics and make some strong claims about how these heuristics are reasonable or are good as compared to the true optimum. And you often see the use of what are called meta-heuristics, which are heuristic methods, but that have been developed to solve a class of computational problems. So it's not a heuristic that's developed to solve one very particular problem, but a class of problems. So things like hill climbing algorithms, or simulated annealing, or genetic algorithms, these are actually heuristic ways to solve optimization problems, and they come from different inspirations, but they also can be applied to any optimization problem, so they're often applied to radio resource management problems. Is an example from a few years ago, through the use of island genetic algorithms to this problem of channel location. So these authors use a protocol model of interference, and an island genetic algorithm divides, so it's inspired by the genetic development and mutation and so on of populations that are segregated for very long periods of time. So the island genetic algorithm in this case divides the population of radios into subpopulations, these islands, and then they interact through the occasional migration of individuals from one island to another, and they try to seek a channel assignment to these various nodes that maximizes the sum of all of the capacity of all of the nodes. So they start with a valid channel assignment, they perform some mutations in some probabilistic fashion, then some crossover of individuals with high fitness function, so highly efficient use of the current spectrum, and then allow the algorithm to evolve, or to, evolve may be the right word in case of genetic algorithms, but so to converge to a solution of channel assignment that's not technically optimal, but that's close enough to the optimum. And there are numerous examples of some of these other meta-heuristics used in the literature as well. And then finally, in terms of techniques to deal with these resource management problems, you have multi-objective optimization. So in multi-objective optimization, you are dealing with a set of objective functions. So no longer one objective function, but a set of objective functions, again with some constraints. There are different ways to deal with this. One would be to combine all of these objective functions into one, and then you're back to classical optimization. So you could have a linear combination of these objective functions with weights associated to each of them. So W1 times the first one plus W2 times the second one, etc. Fine, if you have that, then you're back to your classical optimization function. But then the problem is, how do you assign weights to the various objective functions? How do you combine these into a single one? If you don't combine it, what you're often looking for is what's called the Pareto Frontier for this problem. So just quickly about Pareto Optimality and the Pareto Frontier. So if you're thinking about a assignment of resources to entities that involves some trade-off, so maybe you increase the performance of one, it's going to decrease the performance of the other, or there's a trade-off between performance or cost, some sort of trade-off. Then we say that we have a Pareto improvement if you can move from one allocation of resources to another such that at least one individual in your population is happier than he or she was before, and every other individual is at least as happy as they were before. Okay? So Pareto improvement is where I can make someone happier than they were before without making anyone less happy. So a solution is Pareto optimal if it's no longer possible to make a Pareto improvement on that solution. So you found an allocation of resources that there is no way to change that allocation and increase someone's utility without decreasing at least someone else's utility. If you found that you have a Pareto optimal solution, and the set of all solutions to a multi-objective optimization problem that are a Pareto optimal forms what's called the Pareto Frontier. So maybe it's easier to visualize on a graph. So let's say that I have two objectives. So one in the x-axis and one in the y-axis, and I'm trying to maximize both of them. Okay? And then I have several possible allocations of my resources, which are these green circles. And to each allocation, sorry, I'm really trying to minimize these two objectives, not maximize. So each of these allocations corresponds to one value of objective 1 and one value of objective 2. Okay? You also have something that's called the Utopia Point, which is the point that maximizes each of the two objectives as if the second one weren't there at all. So the Utopia Point can never be reached because I'm basically ignoring objective 1 and then just optimizing objective 2. Then I'm ignoring objective 2, just or minimizing, in this case, objective 1. Okay, so the Utopia Point you can never reach. The only things that you can reach are these points here, and this is the Pareto Frontier. So this is a terrible drawing, but the Pareto Frontier is the set of points where I cannot improve on one objective without hurting another. So these points, the green points are not Pareto optimal because I can always, if I'm here, for instance, I can always move to a different allocation of resources that would make both of my objectives better. So that's not a Pareto optimal point. And if I'm here, similarly, I can move to another allocation of resources that makes both of my objectives better and so on. But on this line lie all the points where I cannot improve on one objective without hurting the other. So that's called the Pareto Frontier. And sometimes all you can do when you have a multi-objective optimization is hope to land on the Pareto Frontier so that you're at least not being inefficient in your use of resources. The other option, as I mentioned earlier, would be to assign weights to these various objective functions and then solve the real optimization problem. And then you're going to select one of these approaches according to the time scale in which the resource allocation must be made. So sometimes an optimization problem implies that you have enough time to reach the optimal and that the system will not change, the circumstances will not change too fast. And if the environment changes very fast, you may want to go for a simpler heuristic that tries to track to do okay, but not necessarily optimally. It depends on whether you're dealing with a problem that's centralized, which may be reasonable to model using classical optimization or multi-objective optimization, or centralized, in which it may make sense to apply game theory or distributed optimization, depending on how the objective functions are, whether they all have a common objective function or if they have separate objective functions, and the complexity of the processing that you can withstand, depending on which node is doing the resource allocation and how much processing power resides in that node. There is the last part of these slides. I may pick up on this in the afternoon. It's talking about radio resource management architectures. And I do want to at least mention, but I won't do it now, the IEEE 1900.4 architecture. But I think it fits well into the discussion of cognitive networks as well. So I'll stop now.